of Life by David Quammen. Read by Jacques Roy.
Three surprises. An introduction. Life in the universe, as far as we know, and no matter how vividly we may imagine otherwise, is a peculiar phenomenon confined to planet Earth. There's plenty of speculation and probabilistic noodling, but zero evidence to the contrary. The mathematical odds and chemical circumstances do seem to suggest that life should exist elsewhere. But the reality of such alternate life, if any, is so far unavailable for inspection. It's a guess, whereas earthly life is a fact. Some astounding discovery of extraterrestrial beings announced tomorrow or next year, or long after your time and mine, may disprove this impression of Earth's uniqueness. For now, though, it's what we have. Life is a story that has unfolded here only, on a relatively small sphere of rock in an inconspicuous corner of one middling galaxy. It's a story that, to the best of our knowledge, has occurred just once. The shape of this story, in its broad outlines as well as its finer details, is therefore a matter of some interest. What happened over the course of roughly 4 billion years to bring life from its primordial origins into the fluorescence of diversity and complexity we see now? How did it happen? By what concatenation of accident and determination did it yield creatures so wondrous as humans, and blue whales and tyrannosaurs and giant sequoias? We know there have been crucial transitions in evolutionary history, improbable incidents of convergence, dead ends, mass extinctions, big events, and little ones with big consequences, including some fateful contingencies that have left behind evidence of their occurrence embedded subtly throughout the fossil record and the living world. Alter those few contingencies as a thought experiment, and everything would be different. We wouldn't exist. Animals and plants wouldn't exist. Why did it happen as it did, and not some other way? Religions have their responses to such questions, but for science, the answers must be discovered and then supported with empirical evidence, not received in a holy trance. This book is about a new method of telling that story, a new method of deducing it, and certain unexpected insights that have flowed from the new method. The method has a name: molecular phylogenetics. Wrinkle your nose at that fancy phrase, if you will, and I'll wrinkle with you. But in fact, what it means is fairly simple. Reading the deep history of life and the patterns of relatedness from the sequence of constituent units in certain long molecules, as those molecules exist today within living creatures. The molecules mainly in question are DNA, RNA, and a few select proteins. The constituent units are nucleotide bases and amino acids, more definition of those to come. The unexpected insights have fundamentally reshaped what we think we know about life's history and the functional parts of living beings, including ourselves. In particular, there have come 3 big surprises about who we are, we multicellular animals, more particularly we humans, and what we are, and how life on our planet has evolved. One of those 3 surprises involves an anomalous form of creature, a whole category of life, previously unsuspected and now known as the archaea. Their name gets uppercased when used as a formal taxonomic category, archaea. Another is a mode of hereditary change that was also unsuspected, now called horizontal gene transfer. The third is a revelation, or anyway a strong likelihood, about our own deepest ancestry. We ourselves, we humans, probably come from creatures that as recently as 40 years ago were unknown to exist. The discovery and identification of the archaea, which had long been mistaken for subgroups of bacteria, revealed that present-day life at the microbial scale is very different from what science had previously depicted, and that the early history of life was very different too. The recognition of horizontal gene transfer, HGT in the alphabet soup of the experts, as a widespread phenomenon has overturned the traditional certitude that genes flow only vertically from parents to offspring and can't be traded sideways across species boundaries. The latest news on archaea is that all animals, all plants, all fungi, and all other complex creatures composed of cells bearing DNA within nuclei, that list includes us, have descended from these odd, ancient microbes. Maybe. It's a little like learning with a jolt that your great-great-great-grandfather came not from Lithuania, but from Mars. Taken together, these three surprises raise deep new uncertainties and carry big implications about human identity, human individuality, human health. We are not precisely who we thought we were. We are composite creatures, and our ancestry seems to arise from a dark zone of the living world, a group of creatures about which science, until recent decades, was ignorant. Evolution is trickier, far more intricate than we had realized. The tree of life is more tangled. Genes don't move just vertically. They can also pass laterally across species boundaries, across wider gaps, even between different kingdoms of life. And some have come sideways into our own lineage, primate lineage, from unsuspected, non-primate sources. It's the genetic equivalent of a blood transfusion, or, different metaphor preferred by some scientists, an infection that transforms identity. Infective heredity. I'll say more about that in its place. And meanwhile, speaking of infection, another result of this sideways gene movement involves the global medical challenge of antibiotic-resistant bacteria, a quiet crisis destined to become noisier. Dangerous bugs such as MRSA, methicillin-resistant Staphylococcus aureus, which kills more than 11,000 people annually in the United States and many more thousands around the world, can abruptly acquire whole kits of drug resistance genes from entirely different kinds of bacteria by horizontal gene transfer. That's why the problem of multiple drug-resistant superbugs, unkillable bacteria, has spread around the world so quickly. By such revelations, both practical and profound, we're suddenly challenged to adjust our basic understandings of who we humans are, what has gone into the making of us, and how the living world works. This whole radical reset of biological thinking arose from several points of origin in space and time. One among them, maybe the most crucial, deserves mentioning here. The time was autumn 1977. The place was Urbana, Illinois, where a man named Carl Woese sat with his feet on his desk before a blackboard filled with notes and figures, posed jauntily for a photographer from the New York Times. The accompanying Time story, for which the photo was shot, announcing that Woese and his colleagues had discovered a separate form of life constituting a third kingdom of biological forms in addition to the recognized two, ran on November 3, 1977. It was front page, above the fold, shouldering aside items on the kidnapped heiress Patty Hearst and an arms embargo against the apartheid regime in South Africa. Big news, in other words, whether or not the average Times reader could grasp from such a lean telling just what was meant by a separate form of life. That article marked the apex of Woese's fame, his Warhol mind. 15 minutes of limelight, then back to the lab. Woese brought radical changes to his own field, to the story of life, and yet he remains unknown to most people outside the rarefied corridors of molecular biology. Carl Woese was a complicated man, fiercely dedicated, very private, who seized upon deep questions, cobbled together ingenious techniques to pursue those questions, flouted some of the rules of scientific decorum, made enemies, ignored niceties, said what he thought, focused obsessively on his own research program to the exclusion of most other concerns, and turned up at least one or two discoveries that shook the pillars of biological thought. To his close friends, he was an easy, funny guy, caustic but wry, with a love for jazz, a taste for beer and scotch, and an amateurish facility on piano. To his grad students and postdoctoral fellows and laboratory assistants, most of them, he was a good boss and an inspirational mentor, sometimes, but not always, generous, wise, and caring. As a teacher in the narrower sense, a professor of microbiology at the University of Illinois, he was almost non-existent as far as undergraduates were concerned. He didn't stand before large banks of eager, clueless students patiently explaining the ABCs of bacteria. Lecturing wasn't his strength or his interest, and he lacked eloquent forcefulness even when presenting his work at scientific meetings. He didn't like meetings. He didn't like travel. He didn't create a joyous, collegial culture within his lab, hosting seminars and Christmas parties to be captured in group photos, as many senior scientists do. He had his chosen young friends, and some of them remembered good times, laughter, fiery barbecues at the Woe's home just a short walk from the university campus. But those friends were the select few who somehow, by charm or by luck, had gotten through his shell. In later years, as he grew more widely acclaimed, receiving honors of all kinds short of the Nobel Prize, Woes seems also to have grown bitter. He considered himself an outsider. He was elected to the National Academy of Sciences, an august body, but tardily at age 60, and the delay annoyed him. He became, by some reports, distant from his family, a wife and 2 children, seldom mentioned in published accounts of his scientific labors. He was a brilliant crank, and his work triggered a drastic revision of one of the most basic concepts in biology, the idea of the tree of life, the great arboreal image of relatedness and diversification. For that reason, Woes's moment of triumph in Urbana on November 3, 1977, has its place near the core of this book. Other scientists and other discoveries are connected to Woes and his tree. A little-known British physician named Fred Griffith, for instance, in the mid-1920s, while researching pneumonia for the Ministry of Health, noticed an unexpected transformation among bacteria, one strain changing suddenly into another strain, presto, from harmless to deadly virulent. This was important in terms of public health. Bacterial pneumonia was in those days a leading cause of death, but also, as even Griffith didn't realize, a clue to deeper truths in pure science.
20 seconds.
The mechanism of Griffith's perplexing transformation remained obscure until 1944, when a quiet, fastidious researcher named Oswald Avery at the Rockefeller Institute in New York identified the substance, the transforming principle, that can cause such sudden change from one bacterial identity to another. It was deoxyribonucleic acid,
Going double file.
DNA. Less than a decade later, Joshua Lederberg and his colleagues showed that this sort of transformation, relabeled infective heredity, is a routine and important process in bacteria, and as later work would show, not just in bacteria. Meanwhile, the corn geneticist Barbara McClintock, discovering genes that bounce from one point to another on the chromosomes of her favorite plant, worked with very little support or recognition through the prime years of her career, and then accepted a Nobel Prize at age 81. Lynn Marcos, a Chicago-educated microbiologist, unique in almost every way, shared at least one thing with McClintock: the frustrations of being dismissed by some colleagues as an eccentric and obdurate woman. In Margolis's case, it was for reviving an old idea that had long been considered wacky: endosymbiosis. What she meant by the term was roughly the cooperative integration of living creatures within living creatures. That is, not just tiny creatures within the bellies or noses of big creatures, but cells within cells. More specifically, Margolis argued that the cells constituting every creature in the more complex divisions of life, every human, every animal, every plant, every fungus, are chimerical things, assembled with captured bacteria inside non-bacterial receptacles. Those particular bacteria, over vast stretches of time, have become transmogrified into cellular organs. Imagine an oyster transplanted into a cow that becomes a functional bovine kidney. This seemed crazy when Margolis proposed it in 1967, but she was right about the matter. Mostly. Fred Sang, Francis Crick, Linus Pauling, Tsutomu Watanabe, and other scientists played crucial parts in this chain of events too, sometimes by force of personality as well as by scientific brilliance. Slightly deeper in the past lie obscure figures such as Ferdinand Cohn, Edward Hitchcock, and Augustin Augier, as well as more famous ones including Ernst Haeckel, August Weismann, and Carl Linnaeus. The ghost of Jean-Baptiste rises here again to skulk along inescapably in the shadows of evolutionary thinking. Such people, all contributors to a scientific upheaval, are of additional interest for the ways their works grew from their lives. They serve as good reminders that science itself, however precise and objective, is a human activity. It's a way of wondering as well as a way of knowing. It's a process, not a body of facts or laws. Like music, like poetry, like baseball, like grandmaster chess, it's something gloriously imperfect that people do. the smudgy fingerprints of our humanness are all over it. Humans aren't the only important characters in this book. There are also a lot of other living creatures whose unique histories and foibles illustrate points in the story I'm trying to tell. Many of them are microbes, those bacteria I've mentioned, those archaea, and other teeny things. Please don't be fooled by their smallness. Their implications and impacts are big. And don't be daunted by their names, which are mostly expressed in scientific Latin: Bacillus subtilis, and Salmonella typhimurium, and Methanobacterium ruminantium, and other monstrous tongue twisters. The reason I call them by those names is not because I like arcane language, but because no other labels exist. Microbes generally don't get the courtesy of common names at the species level. Casual monikers such as southern giraffe, olive bunting, monarch butterfly, and Komodo dragon. If the bacterium known as Haemophilus influenzae could be accurately called Fleming's nose tickler, I promise you I would do it. One other featured character of the human sort should be introduced here. He's a bearded American microbiologist with a penchant for philosophical musing tucked away at a university in Nova Scotia. This man has linked Carl Woese, Lynn Marcos, and much of the new work in molecular phylogenetics into a pungent challenge against biology's central metaphor. His name is Ford Doolittle. He's tall, diffident in manner, though not in thought, and enjoys causing a little intellectual discomfort. At the turn of the millennium, Doolittle published an essay titled Uprooting the Tree of Life, which helped release a cascade of arguments. I caught wind of him through that essay and his related writings, notably those in which he discussed horizontal gene transfer and its implications. Horizontal what? Was my earliest thought. Then I pilgrimed to Halifax and camped for days in his office. Doolittle is semi-retired, still guiding graduate students, still well-funded with a prestigious research grant, but no longer growing radioactive bacteria in the lab in order to deduce bits of their genomes, the totality of their DNA, from images on chest X-ray films. He's no longer pulling chopped molecules through electrophoretic gels as he did in the pioneer days. He reads, he thinks, he writes, he draws. He takes art photographs, mainly for his own amusement, and occasionally mounts a gallery show, but that's another realm of enterprise entirely. In fact, part of what has made Ford Doolittle so influential is that, in addition to his qualifications in biology, he writes far better than most scientists, and he draws deftly, turning big concepts into graceful, cartoony shapes. Doolittle's father was a painter and an art professor. Young Ford considered an art career himself, though his father called that a terrible way to make a living. Then, when he was 15 years old in 1957, the Soviets put Sputnik into space, persuading Ford and many other Americans that science and engineering were the more urgent, forceful pursuits. He went to Harvard College and studied biochemistry. The artistic impulse never left him. Nowadays, to illustrate his subversive thinking and his genial provocations, he draws trees that aren't trees. Woese, Doolittle, Margulis, Letterberg, Avery, Griffith, and the others, they all have their roles in this story, but a more natural starting point is much earlier. London, 1837, with a very different scientist in a very different situation. Part 1. Darwin's Little Sketch. 1. Beginning in July 1837, Charles Darwin kept a small notebook which he labeled B, devoted to the wildest idea he ever had. It wasn't just a private thing, but a secret thing, a record of his most outrageous thoughts. The notebook was bound in brown leather with a tab and a clasp, 280 pages of cream-colored paper, compact enough to fit in his jacket pocket. Portable, but no toss-away pad. Its quality of materials and construction reflected the fact that Darwin was an affluent young man living in London as a naturalist of independent means. He had arrived back in England just 9 months earlier from the voyage of the HMS Beagle. That journey, consuming almost 5 years of Darwin's life on sea and land, mostly along the South American coastline and inland to the plains and mountains, though with notable other stops on the roundabout way home, would be the only major travel experience of his sheltered, privileged life. But it was enough. A mind-awakening and transformative opportunity. It had given him some large ideas that he wanted to pursue. It had opened his eyes to an astonishing phenomenon that demanded explanation. In a letter to his biology professor and friend, John Stevens Henslow, back at Cambridge University, written from Sydney, Australia, Darwin mentioned his puzzling observations of the mockingbirds, not the finches, of the Galapagos archipelago, a set of volcanic nubs in mid-Pacific. These gray, long-beaked birds differed from island to island, but so subtly that they seemed to have diverged from one stock. Diverged? 3 kinds of mockingbird? Varying slightly this island to that? Yes, they appeared distinct but similar, in a way that suggested relatedness. If that impression were true, Darwin confided to Henslow, confessing an intellectual heresy, such facts would undermine the stability of species. The stability of species represented the bedrock of natural history. It was taken for granted and important not just among clergy and pious laypeople, but scientists too. That all the varied forms of creatures on Earth had been fashioned by God in special acts of creation and are therefore immutable was an article of faith to the Anglican scientific establishment of Darwin's era. This tenet is known as the special creation hypothesis, though at the time it seemed less hypothesis than dogma. It had been embraced and supported by prominent naturalists and philosophers of the scientific culture within which Darwin had been educated at Cambridge. He was now home from his wildcat voyage, a youthful adventure with a bunch of rough English sailors, about which his stern father had been skeptical at the start. The experience had altered him, though not in the ways his father may have feared. He hadn't become a drunk or a libertine. He didn't curse like a bosun. Darwin's wanderlust, satisfied physically, was now intellectual. He intended to investigate, very discreetly, a radical alternative to scientific orthodoxy. That the forms of living creatures weren't eternally stable as God had created them, but instead had changed over time, one into another, by some mechanism that Darwin didn't yet understand. It was a risky proposition, but he was 27 years old and deeply changed by what he had seen, and in a quiet way, very gutsy. So he had set himself up in the big city, with lodgings on Great Marlborough Street, a convenient location for his visits to the British Museum. This was just a few doors down from the house where his elder brother, Erasmus, had already settled. Darwin joined scientific clubs, the Geological Society, the Zoological Society, but had no job, didn't need one. The same formidable father who had first disapproved of the Beagle voyage, Dr. Robert Darwin, a wealthy physician up in the town of Shrewsbury, was now rather proud of his second son, the young naturalist well regarded within British scientific circles. Grumpy on the outside, generous within, Dr. Darwin had made supportive arrangements for both brothers. And Charles was single. He sauntered around London. He handled follow-up tasks on his specimens from the voyage. He worked on rewriting his Beagle diary into a travel book, and, very privately, he ruminated about that radical alternative to special creation. He read widely, scribbling facts and phrases into various notebooks. The A notebook was devoted to geology. The B notebook was first of a series on what, to himself only, he called transmutation. You can guess what that meant. Darwin had begun thinking his way toward a theory of evolution. He opened the B notebook in July 1837 with a few phrases alluding to a book called Zoonomia, or The Laws of Organic Life, published decades earlier by his own grandfather, another Erasmus Darwin. Zoonomia was a medical treatise. Erasmus was a physician. But it contained some provocative musings that sounded vaguely evolutionary. All warm-blooded animals have arisen from one living filament, according to Zoonomia, and they possess the faculty of continuing to improve in ways that could be passed down across the generations, world without end. Improvement across generations? Heritable change throughout the history of the world? That was contrary to the special creation hypothesis, but not too surprising from a gouty, libidinous freethinker and sometime poet such as old Erasmus. Darwin had read Zoonomia during his student days and shown little sign of giving his grandfather's daring ideas much credit. But now, on revisiting, he took them as a point of departure. Page 1, entry 1 in the B notebook, his grandfather's title, Zoonomia, followed by reading notes. Then again, those wild suggestions didn't lead anywhere. Erasmus Darwin had offered no material mechanism for the faculty of continuing to improve. And a material mechanism was what young Charles wanted, though he may not have fully realized that yet. As reflected in the B notebook, he now went from his grandfather's work to other readings, other speculations and questions, jotting down clipped phrases, often in bad grammar and punctuation. He wasn't writing to publish. These were messages to himself. "Why is life short?" he asked, omitting the question mark in his haste. "Why is reproduction so important? Why do animals of a given kind tend to be constant in form across an entire country, but to differ at least slightly on separate islands?" He remembered the giant tortoises on the Galapagos, where his stopover had lasted only 35 days, but catalyzed an upheaval in his thinking. He remembered the mockingbirds, too. And why had he seen two distinct kinds of ostriches, his label for big flightless birds, now known as rheas, on the Argentine pampas, one living north of the Rio Negro and one south of it? Did creatures somehow become different when isolated? Put a pair of cats on an island, let them breed and inbreed there for generations with a little pressure from enemies, and who will dare say what result? Darwin wrote. He dared. The descendants might come to look different from other cats, might they not? He wanted to understand why. Another important question. Each species changes. Does it progress? Do the cats become better cats, or at least better cats for catting on that particular island? If so, how long would it take? How far would it go? What are the logical limits if every successive animal is branching upwards, and with different types of organization improving, new forms arising, old forms dying out? That one word, branching, was freighted with interesting implications of directional growth, of divergence, of an arboreal form. And these questions, Darwin asked himself, they applied not just to cats and ostriches, but also to armadillos and sloths in Argentina, to marsupials in Australia, to those huge Galapagos tortoises, and to the wolf-like Falkland Islands fox, all peculiar in certain ways, all unique to their isolated places, but recognizably similar to their correlatives, other cats and tortoises and foxes, etc., elsewhere. Darwin had seen a lot. He was an acutely observant and reflective young man. He sensed that he had seen patterns, not just particulars. It almost seemed, he wrote, that there was a law of adaptation at work. All this and more, facts and speculations, crammed into the first 21 pages of Notebook B. The pages are mostly undated, so we can't know how many days or weeks passed in the opening burst of effort. Anyway, he didn't yet have his theory. Big ideas were coming at him like diving owls. He needed some order as much as he needed the jumble of tantalizing clues. Maybe he needed a metaphor. Then, on the bottom of page 21, Darwin wrote, "Organized beings represent a tree." 2. We don't know whether Darwin sat back after writing that statement and breathed deep with a new sense of clarity, but he might have, and it was entitled. Then he scribbled on. "The tree is irregularly branched," he told the B notebook. "Some branches far more branched. Each branch diverges into smaller branches," he wrote, "and then twigs, hence genera, the next higher category above species, which would be the twiglets or terminal buds. Some buds die away without yielding further growth, species extinction, end of a line, while new buds appear somehow. Although the very idea of extinction had once been problematic among naturalists and philosophers, doubted as a possibility or rejected outright on grounds that God's acts of special creation couldn't be undone, Darwin recognized that there's nothing stranger in death of species than in death of an individual. In fact, extinction was not just natural, but necessary, making space for new species as old ones die away. He wrote, "The tree of life should perhaps be called the coral of life, base of branches dead, ancestral forms gone." Darwin knew something about coral, having seen reefs at Keeling Atoll in the eastern Indian Ocean and elsewhere during the Beagle voyage. They fascinated him. He concocted a theory of how reefs are formed, and in 1842, 5 years after this notebook entry, he would publish a book about coral reefs. Coral seemed apt. Branching coral, not brain coral or table coral, was what he had in mind, because the lower limbs and base are lifeless calcitic skeleton, left behind like extinct forms of ancient lineages as the soft polyps advance upward like living species. But even he seems to have sensed that the coral of life didn't have the same memorable ring. He drew a feeble pen sketch on page 26 in the B notebook of a 3-branched coral of life, with dotted lines depicting the inanimate lower sections, and then he let the coral idea slide, abandoning that metaphor. The tree of life was better. It was already a venerable notion in 1837, and Darwin could adapt it to his purposes as an evolutionary theorist. Easier than inventing a new trope from scratch. Of course, to make that adaptation is to alter its meaning radically. Never mind, he took the step. 10 notebook pages along, he sketched a much livelier and more complex figure in bold strokes, with a trunk rising into 4 major limbs and several minor ones, each major limb diverging into clusters of branches, one branch within each cluster labeled A, B, C, D. The branches B and C were near neighbors in the treetop, within adjacent clusters, indicating close relationships among the creatures on those branches. The letter A was far away, on the opposite side of the tree's crown, signaling a more distant relationship, but still a relationship. The letters were placeholders meant to represent living species, or maybe genera: Felis, Canis, Vulpes, Gorilla. We don't know exactly what he had in mind. Maybe it was nothing so specific. Anyway, this was a thunderous assertion, abstract but eloquent. You can look at the little sketch today with its 4 labeled branches amid the limbs and the crown, and imagine the evolutionary divergence of all life from a common ancestor. Just above the sketch, as though gesturing toward it bashfully, Darwin wrote, "I think." 3. Darwin didn't invent that phrase, the tree of life, nor originate its iconic use, though he put it to new purpose in his theory. Like so many other metaphors embedded deep in our thinking, it came down murkily, modified and re-echoed from early versions in Aristotle and the Bible. Why do these things always go back to Aristotle? Well, that's why he's Aristotle. In the Bible, it's a grand bookend motif, invoked in Genesis 3 just as Adam and Eve are booted out of the garden, and reappearing at the end of Revelation on the very last page of the King James Version. Excellent placement for a launch into Western culture. There, in Revelation 22, verses 1 and 2, the authorial prophet describes his ecstatic vision of the water of life flowing out like a pure river from the throne of God, and beside which grows the tree of life, bearing fruit every month, plus leaves, for the healing of the nations. This tree possibly represents Christ, supplying his leafy and fruity blessings to the world. Or maybe it's grace, or the church. The passage is opaque, and differences in translations, one tree or many, have confused things further. The point here is simply that the tree of life is an ancient poetic image, a resonant phrase, variously constructible, and with a long presence in Western thought. In Aristotle's History of Animals, written during the 4th century BCE, the tree of life is not yet a tree. It's more like a ladder of nature, or as later Latinized from his Greek, a scala naturum. According to Aristotle, the diversity of the natural world proceeds from lifeless things such as earth and fire to living creatures such as animals, little by little, in a progression so incremental that it's impossible to draw absolute lines between one form and another. This idea remained useful throughout the Middle Ages and beyond, turning up in woodcuts during the 16th century as a great chain of being, or a ladder of ascent and descent of the intellect, which typically rose step by step from inanimate substances such as stone or water, to plants and then beasts, then humans, then angels, and finally to God. By that point, it was a stairway to heaven almost 5 centuries before Led Zeppelin. The Swiss naturalist Charles Bonnet reverted to this linear stair-step as late as 1745, even while other Enlightenment thinkers and artists were allowing images of nature's diversity to burgeon sideways with limbs and branches. Bonnet's treatise on insects, published that year, included a fold-out diagram of his idea of a scale of natural beings, arranged in vertical ascent from fire, air, and water, through earth and various minerals, upward to mushrooms, lichens, plants, and then sea anemones, followed by tapeworms and snails and slugs, upward further to fish and then flying fish in particular, and then birds, above which came bats and flying squirrels, then 4-legged mammals, monkeys, apes, and lastly man. See the logic? Flying fish are superior to other fish because they fly. Bats and squirrels exist on a higher level than birds because bats and squirrels are mammals. Orangutans and humans are the best of mammals, and humans are more best than anybody. Bonnet made his living as a lawyer, but much preferred studying insects and plants. He was a lifelong citizen of the Republic of Geneva, his French ancestors having been chased out of France by religious persecution, and so maybe it's no accident that his latter diagram culminated in people, not God. The other notable absence from Bonnet's scale of natural beings, besides God, are microbes. He paid no attention to microorganisms, although the pioneering Dutch microscopist Antony van Leeuwenhoek had discovered the existence of bacteria, protozoans, and other tiny animalcules about 70 years earlier. We all know Leeuwenhoek's name from our reading in high school of Paul de Kruif's Microhunters, a terrible book full of concocted dialogue and bogus detail, but an influential doorway to the subject, or other storybook histories of science, though we might not remember that Leeuwenhoek was a draper in Delft who started making his own magnifying lenses in order to better inspect the thread count of textiles. Then he turned the lenses onto other materials out of sheer curiosity and made astonishing discoveries. He found menageries of tiny creatures living in lake water, in rainwater, and water from drain pipes, even in scrapings of crud from his own teeth. Leeuwenhoek's revelatory observations of microbial life were reported in the Journal of the Royal Society of London and became famous in scientific circles throughout Europe. But Charles Bonnet wasn't interested enough in those very wee animals to fit them into his rising scale, not even where they might dismissively have been slaughtered somewhere between asbestos and truffles. That omission presages a lasting discomfort with placing microbes on the ladder of life, or harder still, arranging their diverse forms on the tree. And it's a discomfort to which I'll return, because it became acute in 1977. The linear approach to depicting life's diversity was on the way out, notwithstanding Charles Bonnet's scale of nature, and being replaced by its more complicated and dimensional successor, the tree. By the late 18th century and the start of the 19th, natural philosophers, we call them scientists, but that word didn't yet exist, tried to classify and arrange living creatures into distinct groups and subgroups, reflecting their similarities and differences into some sort of organizing scheme. The linear alignment, in order of what passed for increasing sublimity, the latter raised toward God, was no longer satisfactory. There had been a knowledge explosion in Europe since the great age of sailing explorations began, knowledge of diverse animals, plants, and other creatures from all over the world, and scholars wanted to set that explosive abundance of new facts within hierarchical categories so that it could be easily accessed and used. This wasn't evolutionary thinking, it was just data management. The knowledge would fill volumes. One man alone, the German naturalist Alexander von Humboldt, published a 30-volume account of his travels in South America, making all the more necessary an overview, an organizing principle that could be apprehended at a glance. An illustration. But the illustrators now needed 2 dimensions, not one, and so the latter turned into a trunk, and the trunk sprouted limbs, and the limbs diverged into branches. This offered more scope, sideways as well as up and down, for arranging the varied abundance of known creatures. The Tree of Life was an old symbol by then, an old phrase, dating back at least to those mentions in Genesis and Revelation. The tree had also served as a model for family histories, the genealogical tree or pedigree of a German duke, for instance. Now, the secularized tree became useful for organizing biology. Among the first to embrace this convention was another Frenchman, Augustin Augier, who wrote in 1801 that a figure like a genealogical tree appeals to be the most proper to grasp the order and gradation of what concerned Augier, the diversity of plants. Augier was an obscure citizen of the French Republic, living in Lyon, working on botany part-time. His real profession was unknown, his biographical details lost, even to a historian of Lyonnese botanists writing 100 years later. Augier disappeared, but he left behind a book, a little octavo volume, in which he proposed a new classification of plants, according to the order that nature appeals to have followed, that is, a natural order, as opposed to an artificial classification system based merely on human whim or convenience. And in the book was a figure representing that system, his arbre botanique, botanical tree. Its trunk and limbs looked almost as orderly and stiff as a menorah, but its sideways branching and copious leafing suggest a rife multiplicity of plant forms. Again, this didn't imply any heretical ideas about origins. Augier was no evolutionist before his time. His natural order wasn't meant to suggest that all plants had descended from common ancestors by some sort of material process of transformation. God was their maker, shaping the varied forms individually. It appeals, and one can hardly doubt it, that the Creator, when making flowers, followed certain proportions and progressions in the number of their different parts. Augier's contribution, as he saw it, was discovering those proportions and progressions, design principles that satisfied the deity's neat sense of pattern, and using them after the fact to organize botanical knowledge into a tidy system. Augier wasn't the first naturalist to hanker for a natural order of nature's diversity. Aristotle had classified animals as bloodless and blooded. In the 1st century of our era, a Greek physician named Dioscorides, attached to the Roman army, gathered lore on more than 500 kinds of plants, arranging them in a compendium mainly on the basis of their medicinal, edible, and perfumatory uses. That book, in various reprints and translations, served as a trusted botany text for the next 1,500 years. Toward the end of its run, around the time of the Renaissance, as people traveled more widely and paid closer attention to the empirical details of nature, old Dioscorides gave way to newer illustrated herbals. These were essentially field guides to botany, graced with better illustrations based on improvements in drawing and woodcut techniques, but still organized for convenience of use, not natural order. In the 16th century, Leonhard Fuchs produced one of those books, an herbal cataloging hundreds of plants, beautifully illustrated and arranged in alphabetical order. 2 centuries later, the great systematizer Carl Linnaeus described a genus of plants with purplish-red flowers, naming it fuchsia in honor of Leonhard Fuchs, and hence we got also the color fuchsia. Linnaeus himself, a Swede who traveled widely as a young man, then took up a professorial life in Uppsala, emerged from this herbalist tradition and went beyond it. Linnaeus's Systema Naturae, as first published in 1735, was a unique and peculiar thing. A big folio volume, barely more than a dozen pages, like a coffee table atlas, in which he outlined a classification system for all the members of what he considered the 3 kingdoms of nature: plants, animals, and minerals. Notwithstanding the inclusion of minerals, what matters to us is how Linnaeus viewed the kingdoms of life. His treatment of animals, presented on one double-page spread, was organized into 6 columns, each topped with a name for one of his classes: Quadrupedea, Aves, Amphibia, Pisces, Insecta, Vermes. Quadrupedea was divided into several 4-limbed orders, including Anthropomorpha, mainly primates, fairy, doggish forms such as wolves and foxes, plus cat forms such as lions and leopards, in addition to bears, and others. His amphibia encompassed reptiles as well as amphibians, and his vermes was a catch-all group containing not just worms, leeches, and flukes, but also slugs, sea cucumbers, starfish, barnacles, and other sea animals. He divided each order further into genera, with some recognizable names such as Leo, Ursus, Hippopotamus, and Homo, and each genus into species. Apart from the 6 classes, Linnaeus also gave a half-column to what he called paradoxa, a wild-card assemblage of mythic chimeras and befuddling but real creatures, including the unicorn, the satyr, the phoenix, the dragon, and a certain giant tadpole, Pseudus paradoxa under its modern label, that strangely, paradoxically, shrinks during metamorphosis into a much smaller frog. Across the top of the chart ran large letters, Caroli, Linnei, Regnum, Animali, his animal kingdom. It was a provisional effort, grand in scope, integrated, but not especially original, to make sense of faunal diversity based on what was known and believed at the time. Then again, animals weren't Linnaeus' specialty. Plants were. His classification of the vegetable kingdom was more innovative, more comprehensive, and more orderly. It became known as the sexual system because he recognized that flowers are sexual structures, and he used their male and female organs, their stamens and pistils, those delicate little stems sticking up to present and receive pollen, for characterizing his groups. Linnaeus defined 23 classes, into which he placed all the flowering plants based on the number, size, and arrangement of their stamens. Then he broke each class into orders based on their pistils. To the classes he gave names such as monandria, diandria, and triandria, 1 husband, 2 husbands, 3 husbands, and within each class, ordinal names such as monogynia, digynia, and trigynia, numbers of wives. Yes, you get the idea. Thereby evoking all sorts of polygamous and polyandrous menages that must have caused lewd smirks and disapproving scowls among his contemporaries. A plant of the monogynia order within the tetrandria class, for instance, 1 wife with 4 husbands. Linnaeus himself seems to have enjoyed the sexy subtext, and it didn't prevent his botanical scheme from becoming the accepted system of plant classification throughout Europe. Our man Augustin Augier, coming along a half-century later with his botanical tree of classification, seems to have seen himself challenging Linnaeus's overly neat sexual system. Stamen number is a striking character, Augier conceded, but not when it comes to the examination of plants. That is, not always unambiguous and therefore not reliable as a basis for organizing the great jumble of botanical life. He nodded respectfully to Linnaeus, also to the French botanist Joseph Piton de Tournefort, who had sorted plants into roughly 700 genera based on their flowers, their fruits, and other bits of their anatomy, and offered his own system, using multiple characters for different levels of sorting and to resolve the ambiguities and fine gradations. This figure, which I call a botanical tree, shows the agreements which the different series of plants